Good afternoon, everyone. So, I am Ainkara Kartika, the TA for this session. So, we will start. So, yeah, so I am Ainkara Kartika, from the Department of Chemical Engineering, IIT Hyderabad. So, I will be handling the live session every Saturday from 3 p.m. to 5 p.m. So, this is for the NPTEL course Computational Fluid Dynamics. The course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras. So before stepping into the course or this week's session, I would like to give an overview of what the course's layout is and how it would be going in the further classes. So in week one, you would have got the video lectures for the course in the NPTEL portal, where the professor would be giving out the lectures. So in week one, you would have seen about introduction to the calculation of flow in a rectangular duct, and in week two, it is about calculation of fully developed flow in a triangular duct. So in week one, it is about a flow in a rectangular duct, whereas in week two, it would be a flow in a triangular duct. And in week 3 it is derivation of equations governing fluid flow, and what are all the equations we would be. What are all the equations we would be using in the CFD, and how we are deriving that. And in week 4 it is about the equations for incompressible flow and boundary conditions. So what the CFD is that we would be discretizing the domain under interest, and we will be solving the equations to get a solution for the same. So in week 5 it is about basic concepts of CFD. So how would we be going about discretization? There are various methods. So one such is finite difference approximation, and in week 6 it is about the basic concepts again, where consistency, stability, convergence, everything would be covered. And in week 7 it is about the solution to the Navier-Stokes equations for the compressible flows, and in week 8 it would be for the incompressible flow solution for while using Navier-Stokes equation, and in week 9 it is solution of linear algebraic methods, algebraic equations for using basic methods, and week 10 it is about advanced methods. So in week 11 we would be dealing with basics of finite volume method including grid generation, and week 12 it is about turbulent flows and turbulence modeling. So these are the books and references. Computational Methods for Fluid Dynamics by Ferziger, and Numerical Computation of Internal and External Flows, HIS, and Numerical Heat Transfer and Fluid Flow by Patankar, and An Introduction to Computational Fluid Dynamics, Finite Volume Method, Verstig, HK, and Malal Sekara, W. So, and last one is Computational Fluid Dynamics by J.D. Anderson, where it covers all the basics necessary for CFD. So before going into that or the course, what is CFD? In order to understand the course, we need to know what CFD is. Till 17th century, there was only experimental fluid dynamics, where scientists worked on large-scale experiments to study the fluid dynamics, and after that it progressed into theoretical fluid dynamics during the 18th and 19th centuries. So with the few models, they studied the fluid dynamics theoretically, and after that with both experimental and theoretical there was need for more faster or improved things to be studied. So computational fluid dynamics came into picture along the 20th century. So CFD is nothing but it is an one more approach in the study fluid dynamics. So it is one more add third approach in the study of fluid dynamics in the our whole discipline of fluid dynamics. So we can say that theoretical fluid dynamics, experimental fluid dynamics, and computational fluid dynamics, everything is essential. We cannot leave out one thing. So, what comprises of CFD or the computational fluid dynamics is that we deal with the engineering or fluid dynamics. The concepts all come from the engineering side, and we need to know the equations and solution for those equations come from. I mean, for those equations. So mathematics also come into picture, and we would be solving all these equations in a computer. So the coding part again comes into picture. So if there is a pre-processed solvers, how I mean softwares, how we go about the fluid CFD studies in those cases is that there are three stages in doing CFD for a particular system. The first one is pre-processing, second one is solving, third one is post-processing. So in pre-processing, what we do is we take the particular geometry and we create the geometry for that particular system, and we mesh that system. In other words, we would be dividing that geometry into small segments, and so that we can write equations for those small systems for the solution purpose. And then we would be solving that, and we would be getting the values at each point. And after that, we would be post processing, where we would be visualizing the results obtained from the solution. So what are all the equations, as we say, what would be those equations? For example, when we consider any physical flows, what we would be dealing out, we would be when we are trying to understand the mechanism, we would be studying the mass conservation, momentum conservation, energy conservation. All these would be expressed in a basic math equations in terms of integral equations or partial differential equations. So what CFD does is it replaces those equations in a simple mathematical algebraic equations for solution purpose. And from those equations, we would be solving them to get the numerical values for the flow fields. And we would be getting the solutions, I mean flow fields for the variables at individual points. From that we can express the system behavior. So what is the advantage when we are dealing with CFD? So why do we prefer CFD? For example, consider we are developing a system. I mean, we are studying a system. So, in order to have knowledge transfer between two people from two different areas, it is not physically possible to carry out that experiment at a different place too, because we can't be carrying the experiments with us, right? So in those cases, CFD act as a transportable tool. We can carry that particular code with us, or like two people can be handling the same code from anywhere with the developed advanced computational resources. So CFD proves useful in those aspects. Like it is cost saving when we are dealing with such like in few cases, and the accuracy is also it is getting increased day by day, and we can understand the complete thing happening inside the system by varying the variables. Like if we vary one variable, what would be the result? That can be studied easily through CFD, and we can develop a model, and we can do safety study and improve the safety in the system. So if we go about the advantages, we need to also know the disadvantages. So the one major limitation would be these, the codes can be sometimes complex, so we need to have a complete understanding of how those things work also, along with the knowledge of the system. And next is the computational resources. Although it is improving these days, computational resources to required to run simulations are not very easily available in the sense we can run a few cases, but it would be again time consuming for us to get the results. And then there would be certain model limitations, like it can or it cannot work out, I mean the codes in for few cases. So we need to be having a complete knowledge on that. And there are like, for if we are going about a system, there needs to be validation that is needed to be carried out. So for those validations again, we need a few experimental data, which again experiment needs to be carried out. So these are all few limitations when we are saying CFD. So it, but again, with the when compared with the disadvantages, we have so much advantages. So because of that, it is widely used in various industries, like we chemical processing industries, almost in mineral processing industries we can simulate any uh, process that is happening in the industry. So we can do scale up studies, and we can like understand what is happening in the industries. And the next is automobile industries, aeronautical industries. I mean aeronautical studies, CFD is very much used, and biomedical and oil and gas hydraulics, everything uses CFD. So that's it about CFD. So since now we would be knowing why we need to study CFD. So that is for going before going into this NPTEL course. So what this session handles is like, we already have the lectures associated for the that particular week in the NPTEL portal. So this problem solving sessions every week from 3 to 5 p.m. on every Saturdays, and one more on one more day as well, someone else is also handling the live session. So what is this, the focus of this particular sessions are that we would be solving the problems that is that would be helping you guys in solving the assignment problems. So these are just problem solving sessions where we would not be going in depth into any of the concepts. We would be dealing with the problems, and if you people have any doubts you can ask. But other than that, these are just to help you guys in understanding the problems associated with that weeks, so that you can easily solve the assignment problems and submit it on time. So in the initial few cases, the problems would be taken from previous years, and if possible, we can also solve that particular week's problem the next week. So that's it. So I think now we can go into the problems for this week. And at any point of time, if you have any doubts, you can just pause me and ask. And also these these videos are being recorded, and they would be uploaded in the link for the same would be given in the NPTEL website too. So you can just check if you have any doubts in the future also. So yeah, we'll now start with the session. So the question 1 is about which of the following formulae is a good approximation for dou square u by dou y square at grid point I comma j. So option A, it is u I j minus, j minus 1 I minus 2 u j comma I plus u j plus 1 I divided by delta y square. Option B, it is uij minus 1 minus 2uij plus 2uij plus 1 by delta x square. Option C, it is uij minus 2uij plus 1 plus uij plus 2 by delta y square. Or option D, it is none of the above. For example, the question is about second order derivative for u with respect to y. So what would be the good approximation for dou square u by dou y square at point I comma j? So if let us consider this is I comma j. This one would be I minus 1. I think I have a picture for this. Yeah. Okay. We can see here itself. So here it is I comma j, the point under our consideration. So what is asked in the question? We need to find the second order derivative, dou square approximation for the second order derivative of u with respect to y at the grid point I comma j. Thing to be noted is we need to know the value at I comma j. So if we remember clearly, we can use it like we are going with respect to y. So delta y is the key point. So we would be going in this way when we are moving, when we are carrying out the points. So it is ij minus 1, that is u ij minus 1 minus 2 u I comma j plus u ij plus 1 by delta y square into 2 is the right answer. So if we look into the options, we can see that uij minus 1 is there, uij 2 is there, uij plus 1 is there, but 2 is missing here. So this is not the right answer. And in the second one, uij minus 1 is there, 2uij is there, uij plus 1 is here, but again delta x square is given, which is false because we need to the question is about dou y square. So the answer is this, which is option B again is wrong. And in option C it is given uij minus 2uij plus 1. Here we are moving with these many points like j plus 1. Here we are going taking one more point and considering it, which makes sense like if the considered point is here uij plus 1, but in the question it is asked that with regard to grid point I comma j. So again here 2 is missing, so again this is false. So answer to this question is option D, that is none of the above. So as we have said, dou square u by dou y square at I comma j is given by this particular formula. So how are we getting this formula? This we can see in the next slide. So there are two approaches which can be used. So in the first one, by using Taylor series approximation, we are getting the values at if uij plus 1, for uij plus 1 we are getting the expansion as this, where uij plus 1 is equal to uij plus dou u by dou y at I comma j into delta y plus dou square u by dou y square at I comma j into delta y square, and so on. And uij minus 1 is given by uij. Here it is plus, since we are going backward, here we have minus dou u by dou y I comma j into delta y plus dou square u by dou y square at I comma j into delta y square, and so on. So now we have two equations. One is for uij plus 1, another is for uij minus 1. So we have to add equation 1 and equation 2. So on adding this, what we will get, uij plus 1 will be there, uij minus 1 will be there, and on this side here we have 2uij, right? We have added, so we have got 2uij. Again this is there, and these two would get cancelled, and again here we would be having 2 times dou square u by dou y square at I comma j into delta y square. So now if we keep this alone in this side and take all the remaining terms, that is 2 delta y square to the right hand side, what we would be getting, uij plus 1 minus 2uij plus uij minus 1 divided by 2 times of delta y square. I think it is clear. So this is what is the right answer, that is dou square u by dou y square at I comma j is equal to uij minus 1 minus 2u at I comma j plus ui comma j plus 1 divided by 2 times of delta y square. So which is not given in option A, B or C. So we have chosen option D, none of the above. So this is one method where of finding out dou square u by dou y square. Another method is this one we would be given in the later lectures. So there are you in numerical methods probably you people would have studied or else. So first one is by employing central difference scheme to find out the first order derivative. Dou u by dou y at I comma j is equal to, since we are using central difference, so we have j plus 1 and j minus 1 divided by 2 times of delta y. So dou u by dou y at I comma j is equal to ui j plus 1 minus ui comma j minus 1 divided by 2 times of delta y. And taking one more derivative, what we would be getting, dou times of dou u by dou y at I comma j, that would give us dou square u by dou y square at I comma j. So taking one more derivative, that is dou times of dou u by dou y by dou y at I comma j. So this is dou times of ui j plus 1 minus ui j minus 1 divided by 2 delta y divided by delta y. So this would be giving us dou times of ui at ui comma j plus 1 divided by dou y minus dou times of ui j minus 1 by dou y, and rest of the term remains. So if we use forward difference for this, dou u by dou y at I comma j, we would be getting it as ui j plus 1 minus ui j by delta y. And for backward difference, uij minus uij minus 1 by delta y. So here we are using this particular formula and substituting it here, and similarly we would be getting dou square u by dou y square is equal to uij minus 1 by minus 2 uij plus uij plus 1 divided by 2 delta y square. This 2 was missing in the option A, that's why option A was not the right answer. So dou square u by dou y square is at I comma j is equal to uij minus 1 minus 2 uij plus uij plus 1 divided by 2 times of delta y square is the right answer. So this is question 1. Now we will go to question 2. In question 2, it is given that consider steady developing laminar flow in a circular pipe. Which of the following statements is true for this flow? Option 1. This question is about, here it is 4 statements are given and we need to identify which of the following statements is true when we are dealing with a steady developing laminar flow in a circular pipe. And of the 4 statements, again options are given to choose which one is the right. So we'll read out the statements first. In first statement, it is velocity profile changes axially. Second, velocity profile changes radially. And option 3, it is pressure varies linearly in the axial direction. Option 4, it is pressure remains constant. So the question, read the question carefully. So in the question it is asked that consider steady developing laminar flow in a circular pipe. So to understand, to find out which of the following statements is true, we need to know how the flow behavior inside the circular pipe would be when we are dealing with a steady developing laminar flow. So we'll just quickly see what the option combinations are given. Okay, so in option A it is 1 and 2, option B it is 2 and 4, option C it is 1 and 3, option D it is 1. 1 only. So answer is given as option A, but before looking into the answer, we should know why it is option A. That is why only 1 and 2 statements are right. So we'll see how the flow profile inside the circular pipe when we are dealing with a steady developing laminar flow inside the circular pipe. So these are all the options given, that is velocity profile changes axially, velocity profile changes radially, pressure varies linearly in the axial direction, pressure remains constant. So we'll see this one is the velocity profile given and this is the pressure equations given. pressure profile. Inside the circular pipe, when we are dealing with the steady developing laminar flow. So this is the laminar flow. So this is taken from this reference paper. So when the before the flow, we know how the velocity profile would look inside the pipe after in the fully developed region. That is, we would be getting a parabolic profile, and we would know that linear pressure drop is developed in the fully developed flow region. So, but while it is in the developing region, before it has attained fully developed flow, what would be the case? So the first option is velocity profile changes axially. So as we can see, the velocity profile is changing axially. So this one is a true statement. Velocity profile is changing axially. So it is the velocity profile is getting changed axially till the time it reaches fully developed flow. It keeps on changing, and the velocity profile changes radially. This again is true, as we can see that it is not constant, right? It is changing radially. And option 3, it is pressure varies linearly in the axial direction. So as we can see that there is a variation of pressure, but it is not an axial variation. So option, that is the third statement, is a false statement. So there is some the pressure is varying, but it is not a proper linear one. So the third statement is a false one. And option 4, it is proven false because pressure remains constant. It is given in the fourth statement, which is completely wrong because pressure is not remaining constant. Pressure is varying. If it had been a fully developed flow, I think the pressure varies linearly in the axial direction would have been true. But the question is regarding before attaining fully developed region. So option 3 is wrong, option 4 is also wrong. So the right answer is velocity profile changes axially and radially is the right answer. So coming back to the question, consider steady developing laminar flow in a circular pipe. Which of the following statements is true for this flow? So option 1, it is velocity profile changes axially. Velocity profile changes radially. Both the statements are true. And third statement, pressure varies linearly in the axial direction, is false. And option 4, it is pressure remains constant, which is again false. So 1 and 2 are the right statements. So accordingly, if we go about choosing the options, option A is the right answer because it has given 1 and 2 as the right. Remaining else are including 3 and 4 as well, which is again wrong. Option D is including only first statement. So again it is wrong. We need to include second statement as well. So answer to this particular problem is option A. This one is the right answer, 1 and 2. So now we'll go to question 3. In question 3, it is given that consider one-dimensional flow governed by d square u by dy square is equal to c over a height h. The interval h is divided into 30 equal segments. The upper wall moves to the right at a speed of 1 meter per second while the lower wall is stationary. The number of discretized equations are. So what the question is, we have one-dimensional flow governed by this equation d square u by dy square is equal to c. So this is the governing equation, d square u by dy square is equal to c for this particular flow, and the region is over a height h. So y is equal to h in this, and this particular region is divided into 30 equal segments. So the upper wall moves at a speed of, so this wall is moving at a speed of 1 meter per second. And this lower wall is stationary. So this one is stationary, so it is not moving. So we can see it is 0 meter per second. And what is it saying? It is divided into 30 equal segments. So how would it be, how many number of discretized equations we would be having? So for example, consider this particular height h, it is divided into 1, 2, 3, 4, 5. So if it is divided into 5 segments, 5 equal segments. Don't mind this diagram or else we can see. Yeah, here let us take it. So here we have consider only the top portion, right? So here what we have 1, 2, 3, 3 equal regions. How many points but we are having in this particular zone? We have 1, 2, 3 and 4. So 4 points we have. Right, for 3 regions, 3 segments, we have 4 points by including the top and the bottom points as well. So the consider one dimensional flow governed by d square u by dy square is equal to c. So when for in CFD the equation given is d square u by dy square. So if we look at the previous question as well, we were discretizing u into some points, right, at I comma j, at I comma j minus 1, at I comma j plus 1, like that. So if in a similar way we are discretizing it, then consider it as we have ui, let this point be j. So this point would be j plus 1 and this point would be j plus 2 and here it would be j minus 1. So according to this particular equation, we know the value of ui comma j plus 2 and ui comma j minus 1 because the wall is moving at a speed of 1 meter per second at the top region, and while at the bottom it is stationary. So we know the values of this and this. So how many discretized equations we are having? We are having 2. So similarly, consider 5 points. Like one more point if we add, we have 5 points. For that we have 4 equal segments. 4 equal segments and we have 5 points. And excluding the top and the bottom one, how many equations we would be having? We would be having 3. So whatever, if it is one more thing is included, again we would be having 5 segments, 1, 2, 3, 4, 5, and we would be having 6 points, out of which we would be excluding 2. So once again, someone, okay. So what I was saying, consider we have 6 points. I mean 5 equal segments. Consider it to be equal, right? One more. So we have 1, 2, 3, 4, 5 segments. And we know the values at these points and this point. So how many points we are left with? We are left with 4. So we can just give a small thing as if there are 6 points, I mean 5 segments, we would be having 6 discretized points and we would be getting out minus 2, that is 6 minus 2, we would be having 4 discretized equations. So accordingly, if there are 30 segments, how many discretized points we would be having? We would be having plus 1, right? 30 plus 1, 31 discretized points we would be having. And how many number of discretized equations you would be having? 31 minus 2, that is n minus 2. This n we are getting by number of segments plus 1, and here we are subtracting minus 2. So the number of discretized equations would be 29. Why are we subtracting 2 from this? Because the top and the bottom, the values are given from the boundary conditions. The boundary conditions specify that the top wall is moving at a speed of 1 meter per second while the bottom wall is stationary. So we know the values at those points. That's why we are subtracting 2 and we will be left out with 31 number of discretized equations. Sorry, 29 number of discretized equations. So answer to this question number 3 is option A. 29 is the right answer, whereas 30, 31, 28 everything is wrong. What is 30 here? 30 is the equal number of equal segments. 31 is the total number of discretized points. Whereas 29 is the total number of discretized equations. So I hope this question 3 is clear. Now we will go to question 4. Okay, in question 4 it is asked that the correct equation governing flow in fluidly developed flow through a rectangular duct is. The correct equation governing flow in a fully developed through a rectangular duct is. The correct equation governing flow in a fully developed flow through a rectangular duct is. So we need to identify which of the following is the correct equation representing the fully developed flow through the rectangular duct. So option A, it is given dou square u by dou x square plus dou square v by dou y square is equal to 1 by mu dou dp by dx. Option B, it is dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dp by dx. Option C, it is dou square u by dou x square plus dou square u by dou z square is equal to 1 by mu dp by dx. Option D, it is dou square w by dou x square plus dou square w by dou y square is equal to minus 1 by mu dou p dp by dx. So we'll see answer to this question is option B, that is dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dp by dx. We'll see how that is. And the correct equation governing flow in a fully developed flow through a rectangular duct. So what we have is we have a flow through a rectangular duct wherein the flow is fully developed. So we need to have the correct governing equation. So for fully developed flow through a rectangular duct, we need to start from the scratch equation. So whatever the problem is, we need to start from this initial scratch equation. So here it is the momentum conservation equation in the x direction. So we are considering flow is occurring in the x direction. So we have v and w velocities are 0. So and u would be a function of y and z. Like u is the x direction velocity. So here we have v and w, which are y and z direction velocities, as 0. And again that particular u is a function of y and z. So the governing equation, momentum conservation equation for flow in x direction is given by this, where rho times of dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus rho g x plus mu dou square u by dou x square plus dou square u by dou y square plus dou square e by u by dou z square. So here we aren't considering the gravitational force, and it is given that fully developed flow through a rectangular duct. So again this u does not vary with velocity, and here it is given that v and w are 0. So this one goes to 0 and w again goes to 0. And what are we left with? Here we have one term, and here we have one term, and dou p by dou x we have. So again it is given that u is a function of y and z. It is not a function of x. So this dou u by dou x would be 0. Dou u by dou x is a 0, and again dou square u by dou x square is equal to 0. If the remaining terms left with can be written as this, in the LHS side everything has become 0. 0 is equal to minus dou p by dou x plus mu times of dou square u by dou y square, and dou square u by dou z square is remaining. So if we take the dou p by dou x to the other side, we are left with dou square u by dou y square plus dou square u by dou z square into mu is equal to dou p by dou x, and again we are taking the mu term to the right hand side. So this becomes dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dou p by dou x. So this is the answer. So on looking in the options, we have dou square u by dou x square, which we have seen. Okay, here if we are dealing with the x direction flow, right? So from this we are identified it as a flow in a x direction, and so it is dou u by dou x would be 0. It would not be the case, and v is 0, so this is not the right term. And in option B it is given that dou square u by dou y square plus dou square u by dou z square, this is the right one. And in option C it is given dou square u by dou x square, which is false. Rest of the term are true, but again one more term is missing, that is dou square u by dou z square. And in option D it is given as dou square w by dou x square plus dou square w by dou y square, which is again false because w is 0 in the x direction flow. So the right answer to this particular question is option B, which is dou square u by dou x, sorry, dou y square, dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dp by dx. Well, that is question 4. Now we'll go to question 5. Consider, in question 5 it is given, consider fully developed laminar flow through a, okay, consider fully developed laminar flow through a square duct of side L and that through a rectangular duct width to height ratio of 2. So for example, we have a square duct. So here the height is L and the width is again L. And in rectangular duct we have width to height ratio is 2. So width is more, sorry, this is rectangular, and on looking at this, what we can say is, if the height is 2, I mean height is L, width is 2L. Okay. Consider fully developed laminar flow through a square duct of side L and that through a rectangular duct width to height ratio of 2 such that both of them have the same cross-sectional area. If the same fluid flows, I mean this is not L, but let us keep some height h, because the cross-sectional area is same in the both. I mean this particular area is same here and here. So that height and length would be adjusted such that if the same fluid flows both the ducts at the same volumetric flow, which of the following statements is true about the two flows? So okay, so what is, we have a square duct and a rectangular duct. Maybe we can keep it like this. So this is length L and this is length L, but this is some 2 height, this is some height h. So the fluid is flowing in the same high, volumetric flow in both the ducts. So in both the ducts we have a fully developed laminar flow through square duct which is having side L, and in the rectangular duct which is having height, I mean width to height ratio is 2, and both of them have the same cross sectional area. I think the same cross sectional area is there. If the fluid flows both the ducts at the same fluid is flowing, if water is flowing in one duct, water is again flowing this another duct, and if it is 1 meter cube per second in one duct, in another duct also the flow rate is 1 meter cube per second. So that is same fluid with same volumetric flow rate is flowing in the both the ducts. So which of the following statements is true? So the first statement is the governing partial differential equation is the same. Statement 2, wall boundary conditions are the same though these are applied at different locations. Option 3, it is flow domain is the same. So we can very well say that since the square duct and the rectangular duct have the same cross-sectional area and the same flow rate, and again the governing partial differential equation is just that since it is a rectangular rectangular square duct, we would be using the Cartesian grids, Cartesian equations. So the governing partial differential equations are same. They would be in u, v, w or with x, y, z planes. So the governing partial differential equations is true. I mean is the same. So the statement 1 is true. Second statement, it is given that wall boundary conditions are the same though these are applied at different locations. That is obviously true, right? Because wall boundary conditions, here we can apply one and here we can apply one. Here if we apply, and that would be different. I mean wall boundary conditions are although they are the same, that is we can apply no slip conditions or full slip, whatever the boundary conditions that we would be applying, they would be the same, they can be the same, but they could be applied at different locations depending on the square and the rectangular duct and their dimensions. And option 3, it is flow domain is the same. Do you think the flow domain is the same? Because flow domain is obviously not the same, because here what we have is a square duct, here what we have is a rectangular duct, and both are having the same cross sectional area, but the height of the rectangular duct is half of the width of the rectangular duct. So the flow domain is not the same between the square duct and the rectangular duct. So option 3, it is false, that is the statement 3 is false. So looking into the options, we have option A, it is 1 only. 1 is true, but it is not 1 only. We have second statement as well is true. So in option B, we have 2 only. This again is true, but again something is missing in option A and B. So in option C, it is given that 1 and 2 only. So this is the right statement where we have the first and second statements to be right. And in option D, it is given that 1, 2 and 3. Third statement, since it is a false, inclusion of that leads to nullifying the option D. So what we have, governing partial differential equations is the same in the both square ducts and rectangular duct problem, and the wall boundary conditions are the same though they are applied at different locations. Locations may vary depending on the geometry of the system, but the boundary conditions are the same. So this is given by option C, that is 1 and 2 only. So I hope this is clear. Now we will go to question 6. Okay, the following few problems are based on this particular case. So based on the given statement, 5 problems should be following up. So we need to read this particular statement carefully and deal with the coming up problems. So in this statement, that is case 1, it is given that you wish to solve a problem involving a steady state heat conduction with a source term. Sorry. Okay. You wish to solve a problem involving steady state heat conduction with a source term. So in case of one dimensional flow, this takes the form k d square t by dx square is equal to q. So q is the source term and we have a steady state heat conduction. So here k is the thermal conductivity. This is the basic equation from the heat transfer course we have studied. And T is the temperature, Q is the volumetric heat generation rate. For this case, answer the following questions. So what is given? You wish to solve a problem involving steady state heat conduction with the source term. In case of one dimensional flow, this takes the form Q is equal to k d square t by dx square, where k is the thermal conductivity of that particular material and T is the temperature, Q is the volumetric heat generation rate. So this is the case. So based on this case, we will be having few questions. So the first question from this particular case is that for equation 1 to be dimensionally consistent, units of Q should be, so here J is given in terms of joules and meters and seconds. So the equation is given in terms of joules, meters and seconds. For equation 1 to be dimensionally consistent, units of Q should be what? So here J is joules, we know it is a unit of energy. So before that, if we see the equations, what we can see, Q is equal to k d square t by dx square. And in the case what is given, Q is the volumetric heat generation rate. So what can we say about that? Q is the volumetric heat generation rate. So if it is a heat generation rate, what unit would it be having? So it would be having joules per second or watts. So watts, if it is, the unit, we would be having joules per second. But what is given in the question, Q is the volumetric heat generation rate. So it is per unit volume, right? So joules per second per meter cube. So that is joules per meter cube second is the right answer. Option D is the right answer. This we can see. I mean, we can say directly by looking. But in the question, it is asked that equation want to be dimensionally consistent. What is the unit of Q should be? So we will substitute the known equations, known units in the equation and identify the unit of Q. So it is given that Q is equal to K d square T by dx square, and K is the thermal conductivity. So what is the unit of thermal conductivity? It is watt per meter Kelvin, and T is the temperature which is in Kelvin, and X is the distance in meter. So we will substitute all the known things in the equation. So it is watt per meter Kelvin into Kelvin by meter square. So this would be like this. So we would be having Kelvin and Kelvin would go, and we would be having watt per meter square. The square. So watt per meter Kelvin into Kelvin by meter square. So Kelvin, Kelvin gets cancelled, and watt per meter cube we have. What is watt? Watt is joules per second. So joules per second meter cube is the right answer. So that is given from option D. Option D, it is joules per meter cube second. So answer to this particular question is option D, joules per meter cube second. Now we'll go to question 7. In question 7, we wish to solve for steady state temperature distribution in a rod of length L. Steady state temperature distribution in a rod of length L, and the variation is only axial, one dimensional. So we have a rod of length L. So the temperature is varying along the axial length. Which of the following boundary condition combination is admissible? So what are all the boundary conditions which can be used? Uh, so we wish to solve, okay, if the temperature is given at both the ends, we can solve the problem for this. Q is equal to K d square T by dx square is the problem. So if it is temperature is known at both the ends, it is possible to solve. And next is heat flux at both the ends. Heat flux is like d square T by dx square at both the ends. If it is given at both the ends, it is not possible to solve. Like if both are derivatives, we cannot be using that boundary, that as a boundary condition to solve. So statement 1 is a true statement, and statement 2 is false. Heat flux and temperature at one end. So if temperature is given at one end and heat flux d square T by dx square at 0. Let us consider x is equal to 0 here and x is equal to length here. So if it is given temperature at one end and d square T by dx square also at the same end, it is not possible to use it as a boundary condition, because what is the use it is making? Think about it logically. We would be getting, we already know the temperature at at that particular end, and if we additionally add heat flux, it does not make any sense. So option, sorry, it is false. It is again false. So heat flux and temperature at one end doesn't make sense. And option, that is fourth statement, is heat flux at one end and temperature at the other end. That is d square T by dx square at one end and temperature at other end. For example, we know the temperature at the exit and d squared by dx square at one end. Then it is possible to use. So actually there are various boundary condition types like we can use a derivative boundary conditions, or we can have constant values boundary conditions. Like for a here example, we have temperature values at the both the ends. Like temperature can be 293 Kelvin here, and temperature can be 323 Kelvin here, or something like that. And in here heat flux at both the ends, d square t by dx square value is given. So there are various names for these boundary conditions, like Newman boundary condition, and so on. Like for each we have a name, so it can be, which could be studied in the later classes actually. Now it is not that important. But logically thinking, what should be known, we need what is boundary condition. For example, let us consider this particular system. Okay, not this, we'll take with the provided example itself. So yeah, we have the rod whose length is L, and the variation is temperature is varying here, like it can be increasing or it can be decreasing or something, right? Temperature is varying and it is increasing or decreasing. So for solving this, we can use discretized equations, right? T at I comma, I mean j comma I plus 1, j comma I minus 1, this is should be I minus 1, this is I, this is I plus 1, I plus 2. Like that we can discretize it into n number of points. So n plus 1 number of points would be there for n equal segments, right? And for that we need to know something. For some base values should be known. For that we need to know the values, some values at the boundaries, that is either at the starting or the end. So because we know the length at that particular, the value of x at that particular locations, and we need to know some idea about how it would be varying, because if we keep candle at one end and we are heating it, we should know what is happening. So for that particular reason we need to know the boundary condition, what should be used at the start and the end. So for that, what combination can be used also matters, right? For example, here we can use the temperature at this end and that end, or else temperature at one end and the heat flux at the other end, because we need to know one value from here and one value from there. So that's what matters. So on that logic, statement 1 is right, statement 2 is not right because we cannot use it to solve the equations, and statement 3 again is false because it is given at one end. Both given at one end, it doesn't be useful. And statement 4 is temperature at one end and heat flux at the other end. So the answer to this particular question is 1 and 4. So option A, it is 1 and 2, it is wrong. Option B, it is 1 and 3, it is wrong. Option C, it is 1 and 4. Option C is the right answer. Option D, everything is given, which again is false. So answer to this problem is option C is the right answer. I hope this is clear. We will go to question 8. In question 8, it is given that for equation 1 to be one dimensional, the term Q can be of which form? For equation 1 to be one dimensional, so the equation 1 is, this is the equation 1. I think I haven't mentioned there. For equation 1 to be one dimensional, term Q can be of which form? Q is equal to constant, Q is a function of x, Q is a function of t, Q is a function of x and t. So it is given that in that particular question itself it was mentioned that steady state heat conduction, so Q is not a function of time. So since it is a steady state, Q is a function of, Q is not a function of time, so Q can be constant. Option 1 is right. Option 2, Q is a function of x is right, because Q is equal to k d square t by dx square is the equation given in equation 1. So that is again a one dimensional equation. Q is equal to k d square t by dx square. So Q can either be constant here or Q can be a function of x. Both the possibilities are only there. Q is not a function of time, because again in the question itself it is given that it is a steady state problem, and again fourth statement is wrong. Q is not a function of x and t. So what are the right statements? Q can either be a function of x or it can be a constant. So option 1 and 2 is the right. So on looking at the options, 1 and 2 is given in A. A is the right answer. B, it is given 1 and 3. It is false because third statement is a false. 1 and 4 again is false because fourth one is a wrong, and D, everything is given, so it is false. So the right answer to this particular problem is option A, that is 1 and 2 is the right answer. So what is Q is equal to K d square T by dx square is the equation 1. So the term Q can be of which form? Q is a like, I mean, it can either be constant or a function of x. Since it is a steady state problem, Q is not a function of t, that is time. So option A is the right answer, 1 and 2. Now we'll go to question 9. In question 9, it is given that which of the following is an admissible extension of equation 1 to steady heat conduction in 2 dimensions. So yeah, what is the equation 1? Q is equal to K d square T x square. So what is given here in equation 1? What would be the thing if it is extended to a two-dimensional problem? So what would happen is that what we would be having is that Q is equal to K d square T by dx square plus d square, I mean dou square T by dou x square plus dou square T by dou y square into K would be what is an extension where Q would be a function of x as well as y. So we'll see what are the given options here. In previous problem itself, what we saw, Q can be a function of x or Q can be a constant. And here, since it is extended to a two-dimensional problem, Q can be a function of x and y, or Q can be a constant. And here, which of the following is an admissible extension of equation 1 to steady heat conduction in a two dimensions problem? So in option 1, it is given K dou square T by dou x square plus dou square T by dou y square is equal to Q x comma y. Here we need to be very much attentive, because in the right hand side Q is a function of x and y is the right. But here K dou square T by dou x square plus dou square T by dou y square, where one K either should have been a common term or it should be coming to y also. So because of the absence of K, it doesn't make sense, because it is not only adding property to the dou square T by dou y x square term, it should also come and influence the dou square to T by dou y square. So option 1 is a false. I mean, it cannot be a right one. In option 2, it is given dou square T by dou x square plus dou square T by dou y square is equal to 1000. So here Q is a constant. Since constant and K is a common term which can be taken out, and again it can be taken into right hand side, and it is a constant again. So Q, this is the right one. Dou square T by dou x square plus dou square T by dou y square is equal to 1000. And in option 3 it is dou T by dou T is equal to alpha dou square T by dou x square. Two things, this is not a two-dimensional term and it is not a steady state equation. So again this is false. So the right answer is option 2, that is second statement is the right one. So we'll see our options. Option A, it is 1, false. Option B, it is 2, right. Option C, it is 1 and 2, false again. Option D, it is 1, 2 and 3, which is again false. Answer is option B is the right answer. Second statement, dou square T by dou x square plus dou square T by dou y square is equal to 1000, because Q can either be a function of x and y and Q can be a constant. In the first statement, although Q is a function of x and y, K is not pulled out as a constant. It is only influencing the dou square T by dou x square, which is false, because it should equally contribute to dou square T by dou x square and dou square T by dou y square. Now we'll go to question 10. These are all the questions, like from 6 to 7, 6, 7, 8, 9. Where are the questions based on case 1. So one case was given, and on the basis of that we had few questions 6, 7, 8 and 9. Now we go to some common questions regarding CFD as well. In question 10, it is asked that you wish to improve the performance of an air-to-air heat exchanger by designing a better intake manifold because the cold airflow is not uniformly distributed across the heat exchanger. You wish to study this using CFD and arrive at better design. For this problem, which of the following statements is true? So in question, we'll read again. So and we'll identify what are all the important things. We wish to improve the performance of an air-to-air heat exchanger by designing a better intake manifold because cold airflow is not uniformly distributed across the heat exchanger. So we have one heat exchanger where cold airflow is not uniformly distributed. Because of that, the air-to-air heat exchange is not getting done properly. We need to have a better design. Uh, so we wish to study this using CFD and arrive at a better design. For this problem, which of the following statements is true? So what is the thing given? We have a heat exchanger. We in the present heat exchanger, cold airflow is not uniform. So we need to or we wish to study this using CFD and arrive at a better or improved design. So what are all the questions? Statements. Option statement A or option A it is you expect CFD to give you a reasonable correct solution. Option B, you expect CFD would not be of much use. Option C, you would look for an analytical solutions. You would rather do experiments. First problem, by thinking logically, we can say CFD would be giving us a reasonably accurate solution. Because what is the purpose of CFD? To, in general, it is like we know the system better, but there is something going wrong in the system, and for that we need to identify what is wrong and arrive at a better design. For identifying that, we would be changing each parameter and doing a parametric study. So we'll be like, if we change this, how much it is affecting the output. If we change this particular variable, how much it is affecting. So this thing we can do in CFD, like we can vary something and find out how the results are varying based on that. So CFD we can use to get a correct, reasonably correct solution. So option A is the right answer because CFD study we can do. Option B it is you expect CFD would not be of much use. Is that so? If we can study and we can get the result, so if we can't say that CFD would not be of much use. So option B is the wrong one. You would look for an analytical solution. So think in this way, we have a large system and we have the equations for those large system. Is it possible to solve the flow equations for that large system analytically? It is not possible. So we should not be looking for an analytical solutions. And option D it is you would rather do experiments. Experiments we can do if it is a single take. However, after arriving at the design aspect, we would be designing that experimentally and studying it in an experiment to see how far this CFD is giving us a better results compared to the previous design. So the final experiment, however, we would be doing, but should we go for like for every parameter change? It is not possible to do experiment. Like here the cold airflow is not equally distributed, uniformly distributed. So if we are changing the airflow nozzle or something, and for each design we can't do experiment. So you would rather do experiments. It is not a wise choice. So which of the following statements is true? We expect safety to give you a reasonably correct solution. So option A is the right answer. Now we'll go to question 11. In question 11, it is given that a client has produced a new catalyst that would improve the rate of a catalytic chemical reaction and wants you to check it out using CFD simulations. For this problem, which of the following statements is true? So what happens? We have a client who has produced a new catalyst or developed a new catalyst to improve the catalytic chemical reactions, and they want us to check it out using the CFD simulations and how it is better behaving or how it is behaving. So for this problem, which of the following statements is true? So option A, it is we expect CFD to give you a reasonably correct solution. Uh, we'll look, we'll come back again and see what is the answer. And option B, it is you expect CFD would not be of much use because you think reaction rate should be specified. Option C, it is you expect CFD would not be of much use because you think flows with chemical reaction cannot be handled through CFD. Option D, you expect CFD would not be of much use because you think flows with catalytic chemical reactions cannot be handled through CFD. So in the first question, first option, it is given that you expect CFD to give you a reasonably correct solution. We generally expect that. But since it is a catalytic chemical reaction and we have a new catalyst, we should at least have some idea about the catalytic chemical reaction that is going on there. So since the client has developed a new catalyst, they should be giving out the information regarding the reaction rate of, kinetics should be known from them. So we expect CFD to give you a reasonably correct solution, but again we need some more information. So option A here is not false, not true. We need some more information, that is what it means. Option B, it is you expect CFD would not be of much use because you think reaction rate should be specified. This is a true statement because we need a reaction rate or we need some information about the kinetics of the reaction. So you expect CFD would not be of much use because you think reaction rate should be specified. Option B is the right answer. And in option C, it is given that CFD would not be of much use because you think flows with chemical reaction cannot be handled through CFD. This is a false statement because we can deal with chemical reactions with CFD. We can mass transfer, heat transfer, everything can be can be dealt with CFD. And reactions as well. Like those would be kind of complex, but it can be dealt with very easily. There are various papers available in the literature, you can go through them, where CFD modeling for the chemical reactions is being done. So option D, it is you expect CFD would not be of much use because you think flows with catalytic chemical reactions cannot be handled through CFD. Again, this is false because it is not that we cannot deal with chemical reactions or we cannot deal with catalytic chemical reactions in CFD. We just need some more information like the kinetics of that reaction. So option B is the right answer for question number 11. Now we'll go to question 12. So in question 12, it is given that you wish to solve a set of linear algebraic equations written in the form of Ax is equal to b using the Gauss-Seidel method. This method will converge if which of the following conditions is satisfied. Matrix A is non-singular. Matrix A, spectral radius of A must be less than 1. Matrix A is irreducible and diagonally dominant. So what happens in CFD is that as mentioned earlier, we have a system. For that we would be discretizing it and we would be having discretized equations in the algebraic form. So we have converted the partial differential equations into an algebraic form. So for the variables would be at each point we would be having ui j plus 1, ui j minus 1 and so on. So this would give us out a matrix. Like we would be having a matrix, for example in the yeah, like in this case we would be having matrix like ui minus 1 j plus 1, ui j plus 1, ui plus 1 j plus 1. Like that we would be having a matrix of unknowns and we need to find the values at those points, right? So we would be generally going with some numerical approach to solve that. So the question is about when Gauss-Seidel is one such method where it is an iterative procedure which you people would have studied in numerical methods course itself. So this iterative method keeps on iterating and we would be getting a solution. So this A matrix, we would be having some values, and in X matrix if we are dealing with the variable u, we would be having u, like u, as I mentioned earlier, it is ui j plus 1, ui j minus 1, ui j minus 2, like that we would be having a list of unknowns. So this A matrix would be the coefficients of them from the discretized equation, discretized equations. So which of the following, I mean, when we are using Gauss Seidel, what is the convergence criteria? So Ax is equal to B, we have written it in the, I mean, with the discretized equations, we have written in the form of Ax is equal to B. So if we need to solve it using Gauss Seidel, what is the convergence criteria? Matrix A is non-singular. Non-singular matrix is that, I mean, the determinant, I mean, for the determinant should be a non-zero for the square. I mean, it should be a square matrix and it should be a non-zero determinant. And spectral radius of A must be less than 1. Spectral radius is that it is the maximum value of the absolute value of the eigenvalues, like maximum value of the eigenvalues for that matrix A. Option 3 is the important one because option matrix A is irreducible and diagonally dominant. So if you remember Gauss Seidel method, the important criteria is A should be irreducible, that it should not be reducible, and it should be diagonally dominant. The diagonally dominant is an important criteria when we are dealing with Gauss Seidel method. So option 3, I mean statement 3 is the only right one. So if we look into it, we have 1, option A is 1, option B is 2, option C is 3. 3 is a false statement. I mean, sorry, 3 is the only right statement. So option C is the right answer. Option D, it is 1 or 2 or 3. No, it is false. 1, 2 and 3, again it is false because 3 is only the right answer. Now we'll go to question 13. In question 13, it is asked that an ideal fluid is one which is an ideal fluid. Option A, it obeys ideal gas law, and option B, it has constant thermophysical property. Option C, it has zero viscosity. Option D, it is none of the above. So which obeys ideal gas law comes under ideal gas? It doesn't mean it doesn't ideal fluid, it doesn't mean that. So what is ideal fluid is that it is both incompressible as well as in non-viscous. Non-viscous is the one ideal liquid, ideal fluid. So it is because because of the non-viscosity, it is smooth because it is irrotational. Like ideal fluid, it is irrotational, everything comes into picture because of the non-viscous nature or the inviscid fluids. So ideal fluid is the one who obeys ideal gas law. No. Has constant thermophysical properties. No. It is has zero viscosity. That is true. And option D, it is none of the above. Not none of the above. Option C is the right answer. That is, an ideal fluid is a fluid that is both incompressible and has no internal resistance. That is zero viscosity, inviscidness, everything. So we'll go to question 14. In question 14, it is asked that an example of a Newtonian fluid is option A, it is air. Option B, it is mercury. Option C, it is glycerin. Option D, all of the above. Newtonian fluid, what is Newtonian fluid? Newtonian fluid is nothing but those fluids which obeys the Newton's law of viscosity. Newton's law of viscosity, it is like tau is equal to mu v by dou x or something. So the shear stress is directly proportional to the velocity gradient. So if we take this take the options given, air is a Newtonian fluid, mercury is a Newtonian fluid, glycerin is also a Newtonian fluid. So options, what would be the non-Newtonian fluids? Like for in day-to-day life, if we see, it is like ketchup and paste, everything. Those things which would be showing some different behavior, shear behavior, comes under non-Newtonian fluid. So for the Newtonian fluid, air is a Newtonian fluid, glycerin, mercury, all the options given here are Newtonian. So answer is all of the above. So we'll go to question 15. So question 15, it is about boundary layer flow approximation applies to option A, it is only to very low Reynolds number. Option B, it is only to high Reynolds number but still laminar flows. Uh, Only to turbulent flows. Option D, it is both B and C. So before going into this, we'll see what is boundary layer approximation. So boundary layer approximation is nothing but we will be approximating the solution of the complete Navier-Stokes equation by some other method. So that is the boundary layer flow approximation. So what is boundary layer? So this is the pipe flow. So in laminar flow would be there, and transition zone would be there, and turbulent regime would be there. So like if velocity profile is like this, it would be developing, right? From here to here it would be developing, and the boundary layer is the one, it would be like this something. So the boundary layer, it includes all the region adjacent to that, all the region adjacent to that particular boundary, adjacent to that boundary would be experiencing the viscosity, and outside fluid is treated as inviscid. So only under this particular boundary layer effects, viscosity would be experienced. So and the outside that region it would not be experienced. That is what the boundary layer states. So where can we apply this? As we can see that in a very low Reynolds number, it is not possible, because here we can see that the boundary layer is covering this and we are not able to use this approximation. Whereas in high Reynolds number but still laminar flows, and in high turbulent flows we can use the boundary layer flow approximation to get the solution, approximate solution for the Navier-Stokes equation or the flow equation, flow governing equations. So it can be used in high Reynolds number but still laminar flows or high turbulent flows. So option C and option B are right. So which is given in option D, that is both B and C are right. Now we'll go to question 16. In question 16, which of the following contributes to viscous drag in a flow over sphere? So, in flow over sphere, consider a sphere is there, and the fluid is flowing over a sphere, and we can see that pressure, what are the contributions from where the viscous drag contributions comes from. So wall shear contributes and pressure variation also contributes. So for the flow over a sphere, both the wall shear and the pressure distribution play a role, and it is both option A and option B is the right answer. So which of the following contributes to viscous drag? Option wall shear and the pressure variation both plays an important role. So option C is the right answer. And in question 17, it is asked that in laminar fully developed flow through a pipe, option the question is about in laminar fully developed flow through a pipe. What are the what are the statements are true from the following? So it is given that just give me 2 minutes break. I'll be back. So actually, before commencing the lecture, a few things like why heat flux at both ends is wrong, because when we are yeah, like when we solve the discretized equation, it would not be used to, because I mean it cannot be substituted directly for if we substitute heat flux in both the ends, it would not be possible to solve them. That is the reason. Um, like the boundary condition types would be dealt in further classes. There you would be getting an more detailed answer, but the reason is when you substitute both the discretized equation in that, you would not be able to get the discretized points. I mean the main objective in the CFD is you should be having the values of the flow variables at each points. So if that is not the possible with the boundary conditions, it is not possible to get in the solution. So it is not advisable to use both. I mean flux. It is not advisable to use the flux boundary condition at both the ends always. So that is the reason we are not using heat flux at both the ends. And yes, you can get the recording and the PPT. Both can be shared from the NPTEL. So derivation of central difference approximation is currently okay. We'll see that. Okay, we'll resume the session. So it's okay. In laminar fully developed flow through a pipe, what is the right one from the given statements? So the first one is axial pressure variation is linear, and option B, it is radial pressure profile is linear. Option C, it is radial pressure profile is parabolic, and option D, pressure is constant. So the question is about laminar fully developed flow through a pipe. So this question, I think we have seen the picture previous case. So we'll go back to there and check what is the right answer. I mean, what is the right answer? Hmm. So yeah, here as you can see, I think we can take it here. Okay. So axial pressure variation is linear. So axial pressure variation is linear. As we can see, it is about a laminar fully developed flow. In previous case, we saw developing flow. Now we should consider the fully developed flow. So in fully developed flow, we can see that axial pressure variation is linear. Linear pressure drop in fully developed flow region is observed. So option A is the right answer. And radial pressure profile is not linear or parabolic. So option B and C are wrong. And in option D, it is pressure is constant. Pressure is not constant. So it is axial pressure variation is linear. So this axial pressure variation is shown from this graph. So it is axial pressure variation is linear in a pipe flow for the laminar case and fully developed case. Because in the previous question it was about developing flow. In developing flow it was not linear. In only fully developed region, pressure axial pressure variation is linear. So answer to this question is option A. Answer is option A is the right answer. And we'll go to question 18. In steady incompressible flow through a converging diverging nozzle, the pressure at the exit section is, so we are having an incompressible flow through a converging diverging nozzle. So we have this converging and diverging nozzle. So pressure at the exit section is, how much the pressure is varying. So first option is highest, second option it is lowest, option C it is lower than the inlet, and option D it is same as the inlet. So since it is a converging and diverging nozzle, we can see that first initially it is a converging and it is a diverging. So whatever the case, from here and here there would be some energy losses because pressure, uh, first it would be increasing and then decreasing as well, but because of the energy losses it would be lower than what value it was at the inlet. So it is not the highest or the lowest, it is lower than the what was the value at the inlet. So option C is the right answer. In steady incompressible flow through a converging diverging nozzle, the pressure at the exit section is lower than at the inlet, because we can apply Bernoulli's equation and we can see that although the energy is lost and regained, it is comparatively lower than what it is at the inlet. So the option C is the right answer, lower than at the inlet. We'll go to question 19. In question 19, it is asked that over 50% of the time spent Over 50% of the time spent in the industry on a CFD project is devoted to the definition of the domain geometry and grid generation. Which one will be the reason for this? Option A, more grids will give better results. Option B, calculation time is directly proportional to the number of cells. Option C, to generate non-uniform grids. Option D, to generate an optimal grid which is the compromise between desired accuracy and solution cost. So this is correctly given that when we are dealing with a CFD project, more than 50% of the time that we are spending would be on mesh generation, geometry creation and the mesh generation. Because recently also one of my seniors told that he has spent almost most of the time in mesh generation than anything else. Solution that and all would be easily achieved if we give the proper mesh. So why do we have to spend that much time? So the option A, it is given more grids will give better results. Again, actually it is not true, because we need to have a proper grid size. If more number of grids means, what does it mean? We would be having a very small grids. So for example, we have this small system. So discretizing meaning, we would be dividing it into small elements or small cells, so that in CFD what we do is, we, as we have seen, we know the value at the boundary. So from here we would be calculating all the immediate points and we will be knowing the intermediate values, and from this we would be using it to get the next adjacent values. Like that it would be converging, or else you be using whole thing at a time and then solving. Whatever be the case, the grids are these: one cell, two cell, three cell. Like here we have how many we have? uh, 1 2 3 and 3 cross 6, so 18 cells we have. So this can further be reduced into this, like the cells can further size can be further reduced. Now how many we have? 1 2 3 4 5 6, 6 cross 6, 36 cells we have. Previously it was 18 and now we have doubled in size. So is it true that this grid would be giving better results than the previous grid? Sometimes yes, but then grid size should not, if it is very low, flow domain also plays an important role. For example, if we are dealing with the particle flows, the grid size should be in proportion with the particles. So it should be containing a single particle or a double particle. Like that, restrictions would be placed. Otherwise, the solution would not be converging to the results and it would be diverging, which again we do not want. So the CFD project, it will be entirely depending on the grid and the mesh. So the domain geometry and grid generation plays an important role. So for that particular reason, why are we spending over 50% of the time? As I said, the most of the time is spent here. So what is the reason? So option A, it is more grids will leave better results. It is not always true. We need a finer mesh, because only then, see, because as I told you, the information is passing from one grid to another. So we need the grid size to be that much finer to have the transport of information from one cell to other, but it should not be so fine that it would again the information passing would be difficult. So one more thing is convergence divergence issue with smaller grids. Another thing would be, think of it this way: when I have 18 points, when I had 18 points, I need to be solving only for this 18. But now I doubled that and I have now 36 points. And if we needed 36 points, the computational resources would be required more. So computational time would be taking that much extra time, double the time. I mean, it is not always directly proportional, but again, calculation time is increased. So more grids may give better results sometimes, but the computational cost would be so high. So that is one reason. And calculation time is directly proportional to number of cells. So this is again true. To generate non-uniform grids are sometimes required, because this in this diagram it is a square grids, and in some different geometry like this, how would we be discretizing it into uniform cells? Here we can be using rectangular or octagonal, I mean hexagonal mesh. There are so many types of meshing only. So it is, all these are true, but why do we spend so much time? Because in these things, if this is the case, like more grids are required or non-uniform grids are required, what we can do is we can directly go ahead and do that same, but we don't know whether we would be getting the solution or particularly right solution or not. So we need right number of grids. So option D is the right answer, that is to generate an optimal grid which is a compromise between desired accuracy and solution cost. So that is the answer, where we should have a compromise between the accuracy. The result should be accurate enough to go ahead with the simulation or to go ahead with the study of that particular system. At the same time, it should not be taking so much uh, computational resources. For example, if it is running for a year, it is possible for some cases. That much time it should not be taking, right? So we need to have an optimal grid size between the desired accuracy and the solution cost. So option D is the right answer. And this is the last question for this day. So in question 20, it is asked that in turbulent flow through a rectangular channel, the flow rate is doubled. Pressure gradient is likely to, option A, remain the same, option B, double, option C, quadruple, option D, 16 times higher. So in question 20, what is asked? For we are having a flow through a rectangular channel and we would be having a turbulent flow. I mean, we are having a turbulent flow. So if we double the flow rate, what is the pressure gradient likely to happen? So here Q1 is there and Q2 is 2 times of Q1, and if it is Q by A is what gives velocity, right? Velocity is equal to flow rate, volumetric flow rate by area, meter cube per second by meter square is meter per second. So V2 is V1 times 2. So flow rate is doubled, and so pressure gradient, if it is del P1, it is approximately proportional to V1 square. So del P2, what would be happening? It is approximately proportional to V2 square, right? So it is V1 square into 4. So answer is 4 times it is likely to increase. So quadruple, pressure gradient is likely to quadruple when we double the flow rate. So in turbulent flow through a rectangular channel, the flow rate is double, pressure gradient is likely to quadruple. So answer is option C is the right answer. So that's it for today. Thank you guys. So this is just an introduction to CFD, because in week 1 I think only few problems were covered, and in from next week onwards there would be more problems from the, like we'll be seeing more problems on the that week's assignment as well. I mean that week's assignment similar problems related to that week's. So this would be, I hope this would help you guys in solving the assignment for week 1. So if there is any doubt you can ask actually. Pressure at the exit will be lower at the inlet due to the pressure due to the adverse pressure gradient when fluid flows from. Okay, thank you. Pressure at exit will be lower than the inlet due to the pressure drop due to boundary layer separation due to the adverse pressure gradient developed when fluid flows from smaller area to larger area. Yeah, thank you for correcting me. Yeah, thank you. If there is any doubt, you can ask, or else that's it for today's session. And yeah, one person has corrected the question regarding that convergence divergence nozzle, where the pressure at the exit will be lower than the inlet because of the boundary layer separation due to the pressure gradient when fluid flows from smaller area to larger area. And I think I represented the information over there, and thanks for correcting. And I think people also see. Yeah, if there is, I'll be here for 5 more minutes. So those who are having doubts, you can ask. Recording and PPT would be shared. The NPTEL would be posting the link for the same, so you can check in there. We would be dealing. I mean, I would upload it everywhere. I mean, the recording and the PPT. So, yeah. Thank you guys for attending. Yeah. Thank you. I'll be closing the session now. Thank you.